Now, let's start. We're going to look at difference quotient, and I am going to do it fairly quickly today, alright?
Sounds good, sir.
Before we go for the,
You got a photos in 10 minutes.
before you go for the photographs. Now, hopefully by the end of the lesson, you can apply the quotient rule to differentiate simple products involving polynomials, negative indices, and radicals. Use the quotient rules to calculate instantaneous rate of change and determine the corresponding equations of tangent lines to graph. You should be able to determine the coordinates of points on graph with specified gradients. Examine simple examples of the quotient rule from graphs or a table. Examine cases whereby both the quotient and chain rules are needed for differentiation, leaving answers in both simplified and unsimplified forms. And finally, solve practical problems in context using the product rules. So I've got 6 questions that I want to go through within 20 minutes. It's going to be a push. Now, if you're given something like this, how would you differentiate?
Chain make it.
Can you use the chain rule?
Well, you got to move it to the top first.
Ah, right. So you put that up there. So can you quickly differentiate that, please? All right, quickly differentiate that, please. So you have 3, 5x plus 2 minus 1 plus minus 1, 5x plus 2 to the power of minus 2, and you've got 5x multiplied by 3x minus 1. All right? Do you agree with me? Hey? Everyone agree with me? Can you simplify that? Can you simplify that? So, if I take the common factor out, which one would be the common factor? Let's say 5x plus 2 to the power of minus 2. So therefore, you now have 3 times 5x plus 2. Correct? So here, if I take this out as a common factor, which means that's 5x plus 2, am I right? Okay, so I'm taking minus 1 here, that will be negative. So this is taken out. I now have 5x times 3x minus 1. Happy with that? So if I rearrange it, I now have 5x plus 2 square, 3 times 5x plus 2 minus 5x times 3x minus 1. Alright, now can you observe that this is actually just a square of the denominator? Correct? Yeah? And the next bit here, what I'm doing is I am taking the differentiation of the numerator multiplied by the denominator. Yeah? Agree?
Yeah.
Then I take away the derivative of this, which is minus 1, 5x plus 2 to the power of minus 2, using your chain rule. And then this, differentiate 5x, that's 5, not 5x. My fault, that's 5. And you've got that 5 times 3x minus 1. Agree?
Yeah.
Yeah? Alright. Now, this is the quotient rule. So given the function defined as a quotient in the form of fx divided by gx, as long as gx is not 0, the quotient rule states that dy dx equals to the first derivative of fx times gx. Take away fx times the first derivative of gx, and then divided by gx all squared. Now, remember, this subtraction and division are not commutative. So the order really matters. Always remember, take the derivative of the numerator first, multiply it by the denominator, then take away the derivative of the new denominator multiplies by the numerator. Then the denominator of the first derivative is the denominator square. Alright? Or in the Leibniz notation, dy dx equals to v du dx minus u dv dx divided by v squared. Be very, very, very clear which one is u, which one is v. So in that case, you could say that that is u and that's v. Alright?
So,
U and v.
oh, 3 minutes. 6 questions. 3.
Alright. Now, this is a challenge, but I'm not going to worry about it. I've run out of time. If you have the time, you can prove the quotient rule using the product rule and chain rule. I've shown you just now using an example, and then prove the product and quotient rules using first principle. That's a challenge. You don't have to do it if you don't want to. Not an issue. Now, can you try doing these two, please? All right? So the very first one, you know dy dx. Something's wrong with my, what? I'll just do it this way. So dy dx, therefore equals to 4x minus 1 all squared. And then I've got the derivative of 3x, which is 3, times 4x minus 1. Take away derivative of 4x minus 1, which is 4. Put a bracket in, so that you have negative, you know what's happening, times 3x. So therefore, I now have 4x minus 1 square, 12x minus 1 minus 12x, which means I've got to take away 1 minus 4x minus 1 all square. Alright, can you try B, please?
Isn't it 3? Yeah, isn't it negative 3? Yeah, over 4.
Negative 3, not 1. Sorry, my fault. Of course, that's 3. 3 times 1 is 3, not 1. All right, try the next one, please. All right. The next one.
It's 2.
Correct. 5x by 3 squared. So now I'm going to differentiate this. However, it might make life a little bit simpler if I change it to x squared minus 2x divided by 5x plus 3. Sometimes it pays to expand. It pays to expand so that you can differentiate the numerator a little bit. It's a little bit more straightforward for you to differentiate the numerator, which is 2x minus 2 times 5x plus 3. Correct? Yeah? Take away x squared plus 2x times 5. Yeah?
Yeah.
So therefore, expanding that, I've got 5x plus 3 all squared, 2x times 5x, which is 10x squared, minus 10x plus 6x minus 4x minus 6 minus 5x squared minus 10x. So therefore, 10x squared minus 5x squared, that will give me 5x squared minus 4x minus 10x minus 6x minus 6 divided by 5x plus 3 all squared.
Isn't it minus 16?
Right. Yeah, happy with it?
Huh?
So what I would do is, I would expand the first one, the numerator. Make life just that little bit easier for you.
So that's
14x.
negative 14x.
14x, yeah, sorry, not 16. Negative 14x. Yep, my fault. All right, let's go on to the next example, please. All right, you do not need to simplify your answer for this one. How are you going to do it?
Rewrite it.
Rewrite it, very good. How do you rewrite that?
Oh, that's just because it's like
So,
this is the function there. It's just like whatever.
I can do dx x to the power of 3 over 2, correct? Minus 2x divided by 1 minus x to the power of 3 over 2. Instead of radical, you don't really, it says here you do not need to simplify your answer. So, once you've done that, it's probably pretty straightforward now. 1 minus x to the power of 3 over 2. That's a denominator square. Alright? You do not have to simplify it. So do not expand. Right? So, what would the numerator be now for the derivative? So here, I would therefore have derived that first. 3 over 2 x to the power of half minus 2. Alright? Multiply that by 1 minus x to the power of 3 over 2. Then take away. Let's derive this. That would be minus 3 over 2 x to the half times x to the power of 3 over 2 minus 2x. Alright? Simplifying, you don't have to simplify that, you can just leave it there.
Because it's a negative x 3 power 3, so when you times it by 3 power.
Alright, you can just leave it there.
That's still negative.
If you want, naturally, for me, I prefer to do it this way. X to the power of half times minus 2 times 1 minus x to the power of 3 over 2 plus 3 over 2x to the power of half x 3 over 2 minus 2x over 1 minus x 3 to the power of 2 squared. I prefer to multiply the negative together so that you get a positive. But again, it is up to you whether you want to do that or not. Alright, because the answer says do not simplify. Alright, let's move on. Happy with this?
Because it says don't simplify.
If you're happy with this, we'll move on to example 3.
Huh?
Alright, example 3. Now you need to determine the tangent to the curve of y equals to x minus 2x minus 3 over x plus 1 at the point 3 and 3 and a quarter. So, what do? You need to find the
Differentiate.
gradient, don't you?
Yes.
Yeah? So finding the gradient,
16.
dy dx equals to
Thank you, bro.
x plus 1
What'd you get for 3?
square. Alright? And then derive the first bit, which is 2
I couldn't fucking
times
solving it. But
x plus 1
5.
minus
16, sorry.
1
That's not that.
times 2x minus 3.
6.
Right. Again, I'm going to stress, because you are not asked to simplify your derivative, do not do that.
In the equation.
Do not simplify, just straight away substitute dy dx, x equals to 3, inside here. 3 plus 1 minus of course 1. This is 2 times 3 plus minus 3.
It's 2x. Wait,
Minus
is it-
3 divided by 3 plus 1 squared.
It's fine.
So therefore you know
Yeah.
this is 8 minus
5.
3 over 16,
Oh,
which
3.
is 5 over 16.
4.
So you now know the gradient at
Yeah, I got it.
that point. So remind you again, using y minus y1 equals to gradient m x minus x1. All right? You know what y1 is? So y take away 3 over 4 equals to the gradient 5 over 16. X take away 3 over 4. All right? So rearranging it, y minus 3 over 4 equals to 5x over 16 minus 15 x over 64.
Wouldn't it be x take 3?
All right. Oh no, hang on, that's 3. Sorry, my fault. That's 3, not 3/4. That's y. Oops. That is 3. So 15 over 16. So therefore, y equals to 5x over 16 minus 3 over 16. All right. It depends on what the question. Sometimes the question asks you to give it in the format of ax plus by equals to d. All right. In that case, what you need to do is rearranging. This will be 5x. Sorry, my fault. 16y minus 5x equals to minus 3. If you're asked to do it in that format, read the question carefully. All right, read the question carefully and make sure that you know what is happening. Are you all happy with that? If so, I'm going to move on to example 4. All right, example 4, you need to determine the gradient at the point where the graph intersects y equals to x plus 2. I am going to try to finish example 5 before we go. So what is the gradient of that at that point? You need to work out. All right, first, what I'm going to do is find the points. All right, I'm going to find the point first. So I'm equating 13x plus 1 over 2x plus 2 equals to x plus 2. Can you solve for x?
Yeah.
Yeah? So multiply both sides by 2x plus 1. Happy with that? So I do have now 13x plus 1 equals to 2x squared plus 4x plus 2x plus 6x plus 4. So therefore, 2x squared minus 7x minus plus 3 equals to 0. 2x and x equals to 0. So here, one would be 1 and 3 minus 2x is minus 6x minus 1x will give you minus 7x. So therefore, x equals half or x equals to 3. Correct? Now, I can straight away find the coordinate, can't I? Which equation will you use?
X plus 2.
Yep. Use y equals to x plus 2. So therefore, y would then equals to 5 over 2. 2 plus 2.5. And y will then be equals to 5. So the two coordinates half, 5 over 2, and 3 and 5. Alright? Now always use the linear. make life a little bit easier. So now you can use find your dy over dx, which is 2x squared plus 2. So I've got 13 times 2x squared, 2x, not 2x squared, 2x plus 2 all squared plus 2 minus 2, 13x plus 1. Alright? So all you need to do is substitute
I like separating.
dy dx, x equals half,
Do you have to like
and dy dx, x equals to 3. Now, so you need to check my calculation at home. I got one of it as 1 over 9. The other one is 3 over 32. Alright? So check that please at home. Make sure that I've got it right. Like I said, I'm going to try to finish this as soon as I can. Then you can go for your photos.
Those look funky numbers.
I think you're right.
Sorry, it is a really fast pace today. If not, I'm going to lose one lesson completely. 5, you need to pay attention to 5. 5 is tricky. 5 is very tricky. Alright? Now, you have got an equation, but you haven't got a clue what k is. So if fx is stationary at 2, 1, determine the value of k. Alright? So, what you need to do is, first, let's find the first derivative of fx. Part A. Can you please work on the first derivative of fx, please? Alright? That's the first one I normally write down when I have a quotient rule. So here, I know I've got k times 1 minus x squared. Take away 2x minus 2x and 5 plus kx. Alright? Now, this time I am going to expand the top because I want to look for k. So I know the numerator is now k minus kx squared plus 10x plus 2kx squared divided by 1 minus x squared. So therefore, we know that you've got kx squared plus 10x plus k equals to divided by 1 minus x squared. Alright? Are you all happy with that? See how I did that? So I use a quotient rule. First, I differentiate 5 plus kx, which means you've got k. Yeah? Times 1 minus x squared. Happy?
Yeah.
And then the next one, differentiate that, is minus 2x. Correct? So I've got minus 2x. I always put it in a bracket. Then multiply by 5 plus kx, which is your numerator. And then denominator is 1 minus x squared all squared. So now, we know that 2 equals to 0. Alright? You know that, you therefore know that kx squared, x, substitute 2 in. So 4k plus 20 plus k divided by 1 minus 2 square equals to 0. Now, you know that this will never be 0 anyway, 1 minus x squared. For that to be valid, so therefore 5k equals to minus 20.
4K.
Oh, hang on. Have I done something wrong?
No, it's 5K.
Yep, 5k is my minus.
Oh, yeah.
Yep, equals to minus 20. K equals to minus 4.
Yeah.
Alright? K equals to minus 4.
Bum.
Alright? So once you know k equals to minus 4, part B, you can determine the values of x for which fx is an increasing function. Now, substitute minus 4 into here. So you've got minus 4x squared. Hang on, let me write it out properly.
Plus 11x.
So, first derivative of fx is minus 4x squared plus 10x minus 4 over 1 minus x squared squared. Right, here, you know that the denominator can never be 0, correct?
Yep.
Do you agree? Denominator can never be 0. So, just using that, can never be 0. If it is 0, that function, that derivative doesn't work.
Yes.
Yeah? Happy? So therefore, what we need to do is look at minus 4x squared plus 10x minus 4 equals to 0. Determine where it is positive. Yeah? So you need to know where it is positive. So here, go back to your year 11 methods. Is this a U-shaped parabola or the upside down parabola?
Upside down.
Upside down. Negative means it's upside down. Correct? So if you determine, let's draw this, sketch it. Don't know what it is like, maybe something like this. Where is it positive? Between the two roots.
Yeah.
Yeah? So can you do that then? So you've got now minus 4x squared plus 10x minus 4 equals to 0. So 4x squared minus 10x plus 4 equals to 0. So solving that, 2x squared minus 5x minus plus 2 equals to 0. 2x, x equals to 0. So 1 and 2 minus minus. So x equals to half and x equals to 2. So you therefore know that this point will be half, this point will be 2. Correct?
Yeah.
Yeah?
Yeah.
Happy with that?
Yeah.
Yeah? So this 2 point here. Here is positive. This point here is there. That point is here. So therefore, this function, when the gradient is positive, is between x, it's greater than half and less than 2. Yeah? This is a tricky one. This is probably a difficult one. All right. Finally, last but not the least, and I know the library is going to kill me for keeping you here. Let's have a quick look at example 6. I will rewrite all this and put it on Google Classroom in a few minutes. My iPad is not working properly just now. All right, now, you need to find the point of intersection between the tangent to the curve at 1 and 2 and the x-axis. So, what you need to do is find the equation, don't you? Yeah? Equation of the tangent line, which is a linear. Yeah? All right? So let's first find the gradient. dy dx therefore equals to, this is 3x squared minus 1 divided by x to the power of half. Correct? So you know, therefore, the denominator will be x. Square root of x squared is x. And then I would have x to the power of half times 6x. Yeah? Take away half x minus half times 3x squared minus 1. Am I going to simplify that?
No.
No, absolutely not, because I'm going to substitute dy, x equals to 1 into the equation, and therefore I know that is 1 times 6 minus, that is half, 3x squared, 3 minus 1 is 2, divided by 1. So therefore, this is 6 minus 1, which is 5. Correct? Remember, in the exam, if you're not asked to simplify, just leave it. All right? The behavior is looking at, use the quotient rule correctly, and then finding the correct derivative. So therefore, y minus 2 equals to 5 x minus 1. Right? So now at the x-axis, y equals to 0. Correct? So therefore, minus 2 equals to 5 x minus 1. Agree? So minus 2 equals to 5x minus 5. So 5x equals to 3. X equals to 3 over 5. So the coordinate is, the point of intersection coordinate is 3 over 5, 0. Yeah? Okay. I have rushed through the lesson, honestly, very, very fast. So if you would all pack your bag, please.